Hello everyone, today I'm going to talk about our work on robust collective classification against structured text. First, some background. Classification is a typical task in machine learning. For many classification models, data points are independent at test time. So what makes collective classification different is that one can also use the relations among data points besides the node features for classification. The motivation behind this is that in many fields, the data can be naturally represented as graphs, and such relations often contain extra information that can be useful for classification. So researchers have developed a variety of graphic models where the input data is represented as an attribute graph. Specifically, X summarizes all the node features and A represents the structural information. So given X and A as input, the graphic models jointly classify all the nodes at test time. While the relation can be used for classification, in many cases it also introduces an extra attacking surface, where the attackers can modify the graph structure. We will term such attacks as structural attacks. Our focus is to develop a robust associative Markov networks against structured text. There are a lot of related works in the field of adversarial machine learning, but most of them focus on models designed for long relation data. There are only a few works on attack and defenses on graph neural networks, for which we will compare in our experiments. So, AMN defines a joint probability distribution of the node labels Y over a graph G. Specifically, X are the node features, W are the model parameters, and P denotes the probability of label assignment Y. There are essentially two tasks for AMN, which are learning and inferring. The problem of learning is to learn the model parameters given a training graph with ground truth labels. This learning problem is formulated as a bilevel program based on the max margin approach. And given a trained model and a test graph, the problem of inferring is to find a label assignment Y with the highest probability. Now I will introduce our robust learning approach on the structured text. So we made some modifications to the original AMN model by incorporating an attacker in the inner optimization problem. The attacker strategy can be encoded as a binary vector E denoting the decisions to add or remove some edges from the graph. Conceptually, given the model parameter W, attacker will find the optimal graph structure that maximizes his objective. This objective serves as a constraint of the outer layer optimization problem. Then the defender's task is to choose the optimal ways under such attack. We can then enforce any linear constraints on the attacker's strategy E into this model, such as some budget constraint. However, solving this bilevel program is not easy. The major technical challenge comes from the fact that the inner optimization problem itself is a nonlinear integer program. And here is the high-level view of our solution approach. First, we linearize the nonlinear terms and relax the integer constraints of the inner program. As a result, it is transformed to a linear program. We then apply the duality of LP such that we can represent the inner program with a set of linear constraints. So overall, we reformulated the bilevel program as a quadratic program. The next question is how good is this approximation approach? We further conduct some analysis on the quantity of approximation. We start with the inner program. Recall that we approximate the nonlinear integer program as a linear program. The optimal solution of the linear program then provides an upper bound of the integer program. So we want to bound the gap between the optimums of the LP and the integer program. Our approach is to use the rounded solution from LP as a bridge. If we can no bound this rounded solution, we can also bound this gap. So the critical step is to round the fractional solutions of LP into integer solutions. We propose a randomized rounding algorithm. The key idea is to assign labels to nodes and edges into faces randomly. We will skip the technical details here. So based on this, we prove that the expectation of the rounded result is low bounded by the blue equation. At last, we can transform the bound on the attacker's objective into the bound on the defender's objective. The details of the proofs are presented in the paper. At last, I will show some representative experiment results. The experiments focus on two aspects, comparing robust AMN with near-range AMN and comparing robust AMN with graph convolution networks and a robust version of GCN. So we test these models on 4 typical relational data sets and under 2 types of structural attacks. One is that the attacker can only delete edges, and the other is that the attacker can delete and add edges simultaneously. So this figure shows the accuracies of AMN and robust AMN on the structural attacks. First, the green dashed line shows the accuracy of AMN on our proposed structural attacks, and the orange dashed line shows the accuracy of AMN on the random attacks. And these differences demonstrated that the structural attacks indeed are threats to AMN. Second, the sorted line shows the accuracies of robust AMN on the 2 attacks, which drops significantly slower. This demonstrated that robust AMN preserves the benefits of using structured information, even the structure can be modified by attackers. Then we compare robust AMN with GCN and robust GCN on the deep attack, which is a structural attack specifically designed for GCN, but has good transferability. Some important observations are that robust AMN is essentially invariant on deep attack, as shown in the red line. GCN and robust GCN are both highly vulnerable to deep attack, as shown in the blue lines, and GCN is also quite vulnerable to our proposed structural attack, as shown in the purple line. At last, we also test robust AMN and GCN on clean data. The results show that their performances are comparable. So for conclusion, we proposed a robust AMN model that can defend against structural attacks. Specifically, we demonstrated that relations could be exploited by attackers to attack collective classifiers. Robust AMN is robust to structural attacks, preserving the benefits of using relational information. And the robust AMN is comparable to GCN on clean data, but is much more robust to structural attacks. And thanks for your attention.